Thank you very much for this opportunity. I'm Takashi Shimokawabe from the University of Tokyo. So I will talk about that today. I will talk about the Miyabi and JCAHPC, the new GPU-based supercomputer and the application porting activity to the GPUs. Okay. So, oh, wait a minute. Okay, it's fine. So here is the content for my talk. So first, I will provide some background on the current trend in the high-performance computing, and then I will talk the road to the Miyabi. After that, I will give an overview of the Miyabi system and discuss the key characteristic of its core component, the NVIDIA GH200. And then I will focus on our activity for the GPU porting. Finally, I will discuss different GPU programming methods and show some performance result. So before I begin, let me briefly introduce myself. So I am now associate professor at the Information Technology Center of the University of Tokyo, and my research topic focus on HPC and GPU computing and the computational fluid dynamics (CFD), and often combined with the machine learning and or maybe now the AI. So I have worked on several GPU porting projects, including the Japan Meteorological Agency with prediction code, as well as the various simulations and analysis code in material science and fluid dynamics and even astrophysics. So let's start with the background. And you can see from the latest top 500 list from the June 2025, you look at the top system like El Capitan, Frontier, and Aurora, and you notice a clear trend. And most of them are all equipped with the accelerators, and that is the GPUs. And this trend is not just about the peak performance. So it's also about the power efficiency measured in the gigaflops per watt. And the GPU-based system dominate the top of the Green 500 list as well. So here in Japan, so we see the same trend with the system like the ABCI and those from the Softman and also the Miyabi. And the GPUs now standard in almost all high-performance system, and their use has become indispensable. So next, I will talk about the road to the Miyabi. And JCAHPC and the Joint Center for Advanced High Performance Computing is a collaboration between the University of Tsukuba and the University of Tokyo since 2013. We introduced this to a big system by combining the budget of the two supercomputer centers. And the Oak Forest packs the OFP with the more than 8,000 the Intel Xeon Phi is the first system of the JCAHPC. And at the first appearance in top 500 November 2016, it was the number 6 in the world and top in Japan. After retirement of the K computer in 2019, and OFE worked as a national flagship in fact until operation of the Fugaku started in 2020. And OFE retired in March 2020 2022, and we are now operating a successor of OFP2, and it's named Miyabi. So this slide and shows the history of the supercomputers at our two university, and so the top is Tsukuba, and the bottom is the University of Tokyo, and the middle line, the collaboration, our universities in JCAHPC. So as you can see, our system has evolved from the CPU-only machines to CPU GPU hybrid systems, and now to the GPU-centric systems. And Miyabi represents the latest step in this evolution. Okay, so the decision to include the computational accelerator was made in the fall of the 2021. So this was considered unavoidable due to the performance demands and the power saving requirement, and also the decarbonizations, and also the rising the electricity cost. So in order to attain the maximum performance under constraint of the electric power consumption, so we are switching to the accelerators, and such as the GPUs is essential in the next 10 years. So this is the table shows the system and the hardware, and also that is corresponding to the gigaflops per watt, the number. So the GPU is very effective. And the selection of the GPU vendor was a critical step in this project, and we made this decision in the June 2022. And this was about 2.5 years before the system launch, which was necessary to give our more than 3,000 users enough time to port their code. And we are evaluated the GPUs from the different vendors using the 7 benchmark code. And these benchmarks include the code that were already GPU enabled and some that were not. The detail is shown in the next slides. And ultimately, so we adapted the NVIDIA GPUs. The key advantage were not just raw performance, but the ecosystem for the application portability, especially for the Fortran code, and which are common in our system. And the programming models like the OpenACC and the standard parallelisms were particularly attractive for helping our users migrate their existing MPI and the OpenMP applications. And this table summarizes the 7 benchmarks for selecting the GPUs. So all of them are traditional simulation code for the computational science and engineering. And the 4 of them are written in Fortran. Okay. So then I would like to give you an overview of the Miyabi system. So this the diagram figure shows overall the system architecture of the Miyabi. The system is composed of two main partitions. The first, this one is the Miyabi G, our accelerated partition, and with the 1120 nodes, and each node is a supermicro server equipped with an NVIDIA GH200 Grace Hopper super chip. And this partition provides the total of the 7.8.8. Oh, here 7.8.8 petaflops. And the second is the Miyabi and our general purpose CPU partitions. And it consists of the 190 Fujitsu primary servers, so each with two Intel Xeon Max CPUs, and providing the 1.3 petaflops in total. And these two partitions are connected by a high-speed InfiniBand NADR network. And for storage, so we have an 11.3 petabyte of flash raster file system. And also, so user can also access the larger than about the 26 petabytes shared storage system called the Ipomoya 01. And let's look at the node in more detail. So the Miyabi G node is based on the NVIDIA GH200 Grace Hopper super chip. It combines the 72 quartz Grace CPU and with a Hopper H100 GPU. A key feature is that the cache coherent the interconnect between the CPU and the GPU. So which I will discuss later. And the Miyabi C here node the features to Intel Xeon Max and 9480 CPUs. Which are notable for their high bandwidth on package HBM2E memory. And so Miyabi, this is the photo of the one node of the Miyabi G, and the Miyabi G is built using the Supermicro's 1U2 nodes servers, and one node here and here. And which is uses direct liquid cooling. And here is the photo of the overview of the Miyabi systems. This is located in the Kashiwa campus of the University of Tokyo. Okay, so and this table compares the Miyabi with as a system at our center, and here is the system, and also the node here that is here is the fee. And the peak memory bandwidth and the result of the stream benchmark and the node power and the result in the GRI 500. So what's the standard at for the Miyabi is it must be massive the peak memory bandwidth over the 4,000 gigabyte per second on the GPU that's here, and also its good power efficiency of 47.6 gigaflops per watt. So this represents significant performance improvement so compared to the previous systems. And the GH200 in the Miyabi is so very, how to say, revolutionary. And because the Grace GPU and the Hopper GPU can directly access each other's memory space, just like a NUMA architecture. So this is enabled by the NVLink, the C2C, and coherent interconnect that offer the over 7 times the bandwidth PCI Gen 5. And it overcome the traditional data transfer bottleneck between the CPU and the GPU. So this not only improves the performance, but also simplifies the programming itself significantly. So it allows us to flexibly assign tasks. For example, so running the small scale or a complex logic on a CPU, while the GPU handles the very heavy computation like this. And from the great CPU's perspective, the entire memory of the CPU and the GPU appear as a single unified address space. And this means that you can use the standard mark, and the location of the memory is determined by which processor, and in this the GPU and the CPU touch it first. And of course, the traditional CUDA memory model with CUDA mark and CUDA mem copy still works perfectly fine, and it benefits from the high-speed interconnect. And from the Hopper GPU's memory view, it can directly access data in the CPU memory using the standard CPU pointers. The behavior of the traditional CUDA code is nearly identical to that on the H100, with the performance scaling according to the memory bandwidth ratio. And this slide is the GH200 memory access. This slide shows the GH200 memory access modes. So the details how different memory types and programming model interact on the GH200 platform. So this unified architecture supports the several memory access modes. So you can use the separate mode, which is which is a traditional mode requiring the explicit data transfer between the GPU and the CPU. And this is the default for the OpenACC and the OpenMP. And you can use the managed or the unified managed here and unified here memory, and where the system automatically migrates data on demand. This is the model used by C++ standard parallelism or std_per. And here is the early result from the 3D Poisson problem. So it compares the performance of the standard H100 GPU and with the Hopper GPU inside the GH200 on our Miyabi system. The key point here is the significant performance improvement of the Hopper GPU itself. So as you can see from the result, and the total execution time for the calculation is much shorter on the GH200. This green bars. And this is the direct result of the architecture advancement in Hopper GPU, and compared to the previous the generation NVIDIA A100 GPUs, so which is depicted in the blue bars. And so for this particularly the memory bound problem, so the performance improved is roughly the 2.6 times, and which is consistent with the increase in the memory bandwidth of the GPUs. Okay, so this chart shows machine hour used by the machine hour in the Miyabi used by the different research fields. So on the Miyabi G, we see the heavy use from the field like the engineering, the material sciences, and the physics, and which I believe which can take full advantage of the GPU's power. And we also see the very growing use for the AI, and of course, then including the large language models. And here is the operational system utilization rate, and the vertical axis is the utilization rate, and the horizontal axis is the year date. And so the overall utilization rate for both the CPU and the GPU resources of the Miyabi system, that is this one and this one, has the very increased currently, and from the launch, and this is I believe indicated the strong demand from our research community. Okay, so next I will talk about our activities for the GPU porting. So here is let's talk about the GPU porting support for the Miyabi. So the number of the GPU equipped supercomputer in Japan is increasing, and the FugakuNEXT, the schedule for around 2030, will also adapt the NVIDIA GPUs, as you know, of course. So, and the Miyabi is the University of Tokyo, the first GPU-centric supercomputer. So to support users in this transition, so we are providing the GPU related workshops and consultation sessions and the dedicated portal site. And GH200 in Miyabi is the ideal for the porting the effort. And I mean the CPU and the GPU can maturely reference each other's memory space, and the CPU and the GPU data transfer is less likely to be a bottleneck. So this changes the traditional porting the strategy, and the old rule was usually we said that put all data on a GPU, and for the GPU, but now an effective approach is to first port the slowest part of the calculation to the GPU and the test of performance. So yes, that. Okay. So the next is the porting the user's code. So the activity for the code porting, so the done under the strong support by the NVIDIA Japan, and because we have more than 3,000 users, and we have the two categories for support. So generally, we recommended the users to port their application to GPU by themselves. This is the self-porting. So when we have the many options, such as 1 week the hackathon, and every 3 or 4 months, and both of online and in person and or hybrid, and the monthly open meeting for the consultation, the via Zoom, and the portal site with the useful information, and but unfortunately that is written in Japanese, but you can see that site from this URL. And we have another procedure, so supported porting. So we are supporting the 19 groups of the 19 groups of the community code and the open form, while we are also prepare the special budget for the outsourcing. And many members of these groups are also attending the hackathon. And so then mostly the users code parallelized by the MPI with the OpenMP. So therefore, the OpenACC with the MPI is recommended for the GPU porting. And this table summarizes the 19 codes for the supported porting, and that is a category. And the point is this is the language that used for the development of the application. And as you can see, the almost all the application are written in the Fortran language. And here is the detail of the GPU hackathon and also the mini camp. So the hackathon and the mini camps have been particularly successful, and these are the intensive event where the participating team that bring their own code and work how to say alongside the experienced mentors from the academia and the industry, and the including the expert from the many Japanese universities shown here, and also the NVIDIA and Fujitsu and the Prometric software. And it's a highly collaborative environment, and many teams have made with significant progress during this event. And so this event have been held approximately 3 times per year since the 2022. And the next event is scheduled to be held around the January in the next year. And we are also offer a variety of the online workshops. For example, this is the one focus on the porting. OpenMP parallelizes the C++ programs to the GPUs. And in this workshop, so participants learn about the different methods from the CUDA to the directives, and the OpenACC or OpenMP, and the C++, the standard parallelisms. And they get hands-on experience using the Miyabi system. And these workshops, including this, are free and open to everyone. So including of course, the university researcher and also the researchers from the industry. And here is the final part of my talk and the GPU programming method and performance. And this is the GPU programming environment list, and there is the wide variety of the GPU programming environment available today. So for maximum the performance on the specific vendor's hardware, so users typically use their native language, like the CUDA and for the NVIDIA GPUs, or HIP for the AMD GPUs. And however, so the vendor neutral and performance portability are becoming increasingly important. And for this, the C++ library, like the SQL here and the Cocos, good choices. And they provide the high-level abstraction that hides the hardware details. And for users who want to easily apply the GPU's acceleration to their existing codes, so the direct-based approach like the OpenACC and the OpenMP OpenMP target are very popular. And So here is the consideration for the GPU programming environment. And the modern, so as you can see, so the modern GPU programming is heavily the C++ based. So like the offshore platform for the NVIDIA, the CUDA, NVIDIA and AMD, the Intel are all C++ based. So and also the high performance portable technology like the Cocos and the SIG are also based on the C++ template and lambdas. So this is the challenge for the many researchers in our community who use the Fortran. So the supporting the migration from the Fortran is a key priority for us, our center, and we are even exploring how LLMs could assist in this process. And this slide show the taste of what the different approach looks like. On the left is the CUDA, and which give you fine-grained control, but is quite verbose, and you have to write a separate kernel and manually managed memory. And the middle is the OpenACC, and you simply add the directives and to you directives, and to your standard the C or the Fortran code, existing code, and tell the compiler which part to run on the GPU. The compiler handles the detail of the kernel generation and data movement. And on the right is the C++ standard parallelisms, or the STD per. So here use the standard C++ algorithms with a parallel execution policy. The compiler is then responsible for the offloading the computation to the GPU. And this approach is very clean and highly portable. And here is the one of the result of the performance. So this graph shows the performance of the Lattice-Boltzmann method LBM, which is one of the CFDR algorithms. And we compare the several modern C++ approach. So that's expected. So the hand-tuned the CUDA, this particular access is the performance, and the higher is the better performance, and hand-tuned the CUDA and give the best performance. So on the other hand, the implementation using the STD per here and the OpenACC, the here yellow bars provides higher level of abstraction and portability, but their performance remains at about the 70% of the achieved by the CUDA implementation. And another good option for the portability is Cocos. I said so. The Cocos is the C++ library that provides the program model for the writing the performance portable applications. And you write your code once using Cocos, the parallel pattern, and the data structures. and it can then be compiled to run efficiently on March core CPUs and NVIDIA GPUs, AMD GPU, and so on. And it achieved this by using the different backend, like the CUDA, the HIP, or OpenMP, or SQL. And the University of Tokyo is now a member of the High Performance Software Foundation, and which supports the COCOS, and we are actively promoting its use in our community. And here is the preliminary performance comparison on the GH200. The GH200 is in Miyabi node. And this test is the main kernel of our LVM code, and the buffer, the left, shows the performance of the COCOS code running on the Grace GPU using the OpenMP backend. And the other three birds, here and here and here, show the performance on the Hopper GPUs. The COCOS, the CUDA bird, is the performance of the portable COCOS code compiled with the CUDA backend. And so it is about the backend, and the CUDA, that this is CUDA, that is the original one, and it's our hand-tuned CUDA code. And finally, the COCOS with the optimization is the COCOS code there after applying some simple portable optimization, like accessing data through raw pointers instead of the COCOS builds. So as you can see, the optimized the COCOS code achieved almost the same performance as the hand-tuned, the non-portable CUDA code. And this is a very good result, and it demonstrates that you don't have to sacrifice the performance to achieve the portability. Okay, so to conclude my talk, so the JCAHPC launched its new supercomputer Miyabi in the January in this year, equipped with the NVIDIA GH200. And this is tightly integrated CPU and GPU architecture of the GH200 is a key feature that simplifies the programming and the boosts the performance. And we have established the comprehensive support system, including the hackathon and workshops, to help our large user community migrate, porting their application to the new Miyabi platform. And finally, so while many programming methods exist, we have shown the modern performance portable C++ library like COCOS, the practical and powerful solution for the GPU application development, enabling researchers to write a code that runs effectively across the different architectures. So, thank you for your attention, and be happy to answer any question you may have. Thank you very much.